Okay, in this section, we are going to explore the idea of transformations of graphs. So we have some idea of functions and how to use function notation to describe a function and how to create the corresponding graph using points. What we're going to look at here is how changes to the function formula impact the graph of the function. So in order to do that, the first thing we need to do is build a library of basic functions. We're going to call these the parent functions. And we will utilize these to then examine how changing their formulas impacts the way that the graphs appear. So the first function that we want to be familiar with is a linear function, a basic linear function. These are in the form mx plus b, and so we know that m indicates the slope or the steepness of the function, and then b is going to tell us the y-intercept of that graph, which is, we know from our previous work, where it crosses the y-axis. So when we look at these functions, we can tell that, assuming there's arrows on the end of these, that the domain is all real numbers and the range is all real numbers as well. That steepness indicates that even though we can't see it in this small picture, that this graph will eventually hit all possible y values, so its range is infinite. A very specific case of the linear function is the constant function f of x equals b, and that is where the slope is 0. So we have an m value of 0 here, and the slope is, it's a horizontal line crossing through, again, the y-intercept of b. And here we also see that the domain is negative infinity to infinity, but the range is very, very different. Here the only y value that we hit is b, so that means that our range is just the value b. So similar to the linear function, but with a really distinct range. Then we have another special case of the linear function, which is the identity function, f of x equals x. This one here, notice that the slope is 1. It's as if there's an invisible 1 in front of that x. And then we have the b value, the y-intercept is 0. We're adding 0 onto there. So if we rewrite it as 1x plus 0, it looks a lot like our linear function, which means that it also has the same domain and range as the general linear function from before. All right, so that covers the linear functions. Then we've looked at the idea of absolute value as being distance from 0, and we know that absolute value always has to be a positive number, which means that when we graph absolute value, we get a graph that is only above the x-axis. All of the outputs are positive. If we were to make a table of values for this, with x and f of x equals absolute value of x on the left and f of x equals absolute value of x on the right, we could, if we include a couple of positive and negative numbers, we would see that the outputs are all positive numbers, which is reflected in the graph. What that means then is that our domain is negative infinity to infinity, but our range is only positive numbers. So our range starts at 0 because we have this point right here at the origin that hits 0, but then it goes up to positive infinity. We're going to see absolute value a lot, so it's a really good idea to commit what the graph looks like to memory, as well as to be able, if you forget the shape of it, to be able to crank out a table that has values that will be helpful in drawing the graph. All right, another one we're going to see a lot is the quadratic function. So here we're going to look at just the basic quadratic, which is the graph of f of x equals x squared. And if we look at a table of values for this, we'll have x and x squared in our table. Again, I'm going to just choose a few select positive and negative numbers because we know we can square all of those. And when I do that, I get 9, 4, 1, 0, 1, 4, and 9. And those points are reflected. There's the 0, 0. Here I have 1, 1, and negative 1, 1. And then I have 2, 4, and negative 2, 4. And negative 3, 9, and 3, 9 are too high to be actually on this graph. But you can see where this graph gets its shape from. And again, similar to absolute value, we have a domain of all real numbers. And the reason why is because any real number that you name, we can square it. So the domain is everything. But when we square real numbers, two negatives make a positive. So our range is once again just the positive numbers, 0 to infinity. This one, again, you should get very familiar with it. We're going to see the squaring function over and over and over throughout the course. The cubic function is a good one to know as well. It is one that if you are ever looking for an example of an odd function, a cubic function is a good one to have handy. Here our values would look like this. I'm going to start a little bit smaller just because the cubic function gets big pretty quickly. So when x is negative 2, if I cube that, negative 2 times negative 2 times negative 2, I'm going to get a negative number this time because cubing allows us to get negatives. Negative 1 cubed is going to be negative 1, 0 cubed is 0, 1 cubed is 1, and then positive 2 cubed is going to be positive 8. And so we can't even get 2, 8 is somewhere down here, or negative 2, negative 8, and positive 2, positive 8 is up here. Here's 1, 1, negative 1, 1, and 0. And so we get this shape for the cubic graph. And this one is another function that has as its domain negative infinity to infinity, and also the same range because the cube does allow us to spit out negative numbers when we input a negative number. All right, now we're going to see our first function that has a restricted domain. So when we're talking about functions in this class, we always assume that our inputs have to be real numbers and our outputs have to be real numbers. We know that if we attempt to square root a negative number, the output is an imaginary number, not real, which means that we have to restrict the domain. In order to be able to graph it, we have to be able to restrict the domain of the square root function to only positive numbers. So our domain here is 0, infinity. Then when we use this notation, right, we all know that if we're trying to figure out the square root of a number, it generally has two answers, right? The square root of positive 9 is both 3 and negative 3, because if I square either of them, I will get positive 9. However, when we're talking about functions, we have to remember that each input can only give one output. So we have to pick a square root if we want this to be the function. So generally, it's convention that when we see the square root in a function, we assume it is the positive square root. If instead we want to take the negative square root, we would rewrite it with a negative sign in front of it. So this means positive square root. And that's a convention that we can just assume going forward. If we want the negative square root, we would actually write it like that. So since the one we have here in front of us is the positive square root, we know that all of its outputs have to be positive numbers, which means the range of this function is always 0 to infinity as well. Now, this one is, again, another one we'll see fairly often, so it's really handy to have a set of points that you can use to construct the graph. So here what I'm going to do is I'm going to very carefully choose my x's so that when I take the square root, I get a nice integer. So the square root of 0 is 0, so that one works. The square root of 1 is 1. 2 does not have a nice integer square root. It's, I think it's like 1.4 something. 3 doesn't either, but 4 does. 4 has a nice square root of 2, and we can see that point right here on our graph. There's the point 4, 2. And then if we had some more space, we could maybe go all the way out to 9 because it has a square root of 3. So these tables I'm putting in here are not meant to indicate that these are the only x values we can plug in. I'm just choosing them so that we have nice ones that when we try to recreate the graph, if we've forgotten its shape or for other purposes, we have some nice values that we can plug in to get back to the shape. The cube root graph here looks like we kind of took the cube function and turned it around a little bit. The cube root graph, we can see from the picture, also has, just like the cube function, has a domain of negative infinity to infinity and a range of negative infinity to infinity. And here, this is not one we use particularly often throughout the course, but it's good to know. Again, I'm going to pick x values that I know have nice cube roots, so maybe -8, and that's going to be 2 cubed. So the cube root of -8 is not +2, but -2, and that point would be way over here somewhere. And -1 has a nice cube root of -1. That's this point here. 0 has a nice cube root of 0. 1 has a nice cube root of 1, and then +8 has a cube root of 2, which again would be off of our graph somewhere to the right. All right, one last function that we will see is, this one forms the basis for a lot of the rational functions that we're going to deal with. It's the function 1 over x. 1 over x, we know if we try to stick a 0 in there for x, then we're going to be divided by 0, which does not make a real number. That is undefined. And so that means we have to eliminate 0 from the domain. Every other x value works, though. Every other x value will make a fraction or a whole number or a decimal. It will spit out a real number. That's the important part. So 0 is the only thing that isn't in our domain. So to write that, we're going to say we go from negative infinity to 0, and then we'll use parentheses to indicate don't include 0. That's all the stuff that's smaller than 0, and then to write all the stuff that's bigger than 0, again, we start with the parentheses for the 0, saying don't include the 0, but include everything that's to the right of it, and we go up to infinity. Our range is similar. 1 over x can never equal 0. There's no value of x that will make that equal 0, so our range is identical here. And if we want to think about some key points on this graph, maybe we'll take, let's use some fractions here. So let's take like -2, -1. Let's look at -1/2, 0, 1, 1/2, and 2. I'm just picking them to be symmetric across the axis for no reason other than, I don't know, makes it look kind of nice. So this is going to give us -1/2, and we see that point right here. This would give us -1, that's right here. And then notice if I do 1 over -1/2, 1 over -1/2 is the same as 1 times, we flip over the bottom, and we get 1 times -2 over 1, which is -2. So when we plug -1/2 into this function, we actually get -2, and we can see that right here. There's -1/2, -2. At 0, well, I shouldn't even have put 0 in there because that's undefined. We already said that's not even in our domain. At 1, we have 1 over 1, which is 1. At 1/2, it's going to be the same thing, 1 over 1/2. We're going to flip that denominator, we're going to get 2, and then 1 over 2 is 1/2. And those points are here, that's 1, 1. Then we have 2 1/2 over here, and then at 1/2, we're up at 2 right there. So those points are in the graph. All right, now that we're familiar with that group of functions, we're going to start to look at is what happens when we make small changes to their formulas and what impacts those have on the graph. So the first set we're going to look at are going to be shifts. We're going to look at horizontal and vertical shifts. So vertical shift means we're shifting up or down. And if you think about what that means, this is up or down. When we shift up or down, that means our y coordinates are moving, but our x coordinates are not. So the way we recognize a vertical shift is we're going to take our parent function, f of x in this case, we've got a function f of x, and then we're going to let c and h be the constants that we use. So if we add f of x or subtract, if we add or subtract c to f of x on the outside of the function, so something like x squared, there's our parent function, x squared plus 2, or x squared minus 2. That is going to result in a shift up or down. So plus c is a shift up, and f of x minus c is a shift down. So these kinds of shifts are going to result in changes to our y coordinate. In other words, if the point a comma f of a is on our original graph, then the point a comma f of a plus c is on our new graph after we perform the transformation. So we can, if we can identify points on the original graph, then by changing their y coordinates, we can figure out what the effect of the vertical shift is going to be. And of course, if it's a subtraction, we would just subtract there. Horizontal shifts are a little bit different. We're going to recognize these as looking like f of x plus c with the plus inside the parentheses, or f of x minus c with the plus on the with the minus on the inside of the parentheses. So in comparison to what we had before, x squared plus 2 and x squared minus 2, these are going to look like x plus 2 all squared and x minus 2 all squared. And the key difference here is that when the shift happens on the inside of the parentheses, that means that we are moving left or right. So, and it's a little counterintuitive, but f of x plus c, this is going to be a shift to the left. F of x minus c is where we shift to the right. So if the point a, f of a, is on our original graph, then the point a, if we're shifting left, the point a minus c, f of a, is going to be on our new graph if we have a plus in the middle. I know it seems strange, but we actually subtract c from the x-coordinate to get the shift to the left. That is represented by f of x plus c. And if a, f of a, is on our original when we have subtraction, this time we're going to add c to our x value to figure out which points might lie on the new graph. So let's look at an example. Here we have two functions, g of x. They both involve a square root. One of them, g of x, says take the square root of x and then add 2 to that value. F of x said take x, add 2 to it, and then take the square root. And we're going to see that these look very different. We can tell for both of them that they start off with the function square root of x. I'm calling that p of x for a parent function. And if we think back to what we learned about the library of functions, we know that the points 0, 0, 1, 1, 4, 2, and 9, 3 are all on the graph of p of x. And so I'm going to go over here and I'm just going to plot those points and sketch a little graph of p of x. So this gray picture is p of x. And now we're going to examine what happens when I take p of x and I just add 2 to it. So this right here, this plus 2, is on the outside of our parent function. Outside the parent function means we're impacting the y coordinate. This is a vertical shift. We're going to shift up. So for g of x, this is a shift up. Up or down means y coordinate is changing. So what I'm going to do is I'm going to apply the transformation, the plus 2, to the y coordinates on my original points. So I'm going to keep all of my x's the same. Those points, those x coordinates are still holding true, but their y coordinates shift up by 2. So now I'm going to go through the points 0, 2, 1, 3, 4, 4, and 9, 5. And so when I graph that, 0, 2, 1, 3, 1, 2, I'm having trouble counting to 3, 4, 4, and I can't fit 9 on there, but we're going to see that the graph has the same shape as it did before. It just looks like we picked it up and shifted it up 2. Okay, let's compare that to f of x. For f of x, this is a shift to the left. Because if you think about it, our original value, our original function, when x was 0, the square root was 0. In this function, in order for it to spit out a value of 0, x would have to be equal to -2. So that's where the left shift is coming from. So what we're going to see here is that for each of our original points, I'm using these points again here, the original points on the graph. Now my y-coordinates don't change at all. 0, 1, 2, and 3. But my x-coordinates are all getting shifted to the left, which means I'm subtracting 2 from them. So it's going to look like -2. 1 minus 2 is -1, 2, and 7. So that corresponds to this picture over here, -2, -1, 1, 2, 2, and 7, 3, which looks like this. So now we can see that we took the graph of the square root function and we shifted it over to the left some. And you can check for yourself if you take each of these x-coordinates. Let's pick one. Let's take -2 and let's plug it in here. That gives us the square root of 0, which is in fact 0. If I take -1 and I plug it into f of x, I get the square root of -1 plus 2, which is the same as the square root of 1, which is 1. So the points we have here correspond to our function definition. So there is an example of shift left or right. All right, here we're going to see the same idea with a slightly different parent function. So this time we're going to let p of x be x squared. This is our quadratic parent function. And I know that because I see x squared here and x squared and a square there, which is what tells me that this must be my parent function. And that was the one that went through 0, 0, 1, 1, -1, 1, 2, 4, and -2, 4. So I'm just going to sketch those points in and draw a little picture of our original parent function for us to work with on both of these axes. Whoops, I did not make those last 2 points high enough. I thought that looked weird. 2, 4, -2, 4. All right, there we go. All right, and so now let's look at what our shifts do. So we can see in h of x that the -2 is happening outside of the parent function, right? First we square, then we subtract 2. That means h of x is going to be a shift, oops, looking for a different color. It's going to be a shift down by 2. Right. And so if we think about those points that are on our original graph, I said them before, but I didn't write them down. So let's write them down. -2, 4, -1, 1. That's -2. It's hard to read. Let me just erase it so you can read it. 0, 0, 1, 1, and 2, 4. So when we shift down, we have to remember that a shift down means our x-coordinates stay the same. Our y-coordinates get 2 subtracted from them. So we're going to do 4 minus 2, and then 1 minus 2, and then 0 minus 2, and then 1 minus 2, and then 4 minus 2. And so when we graph those points, we'll see that this thing has, in fact, shifted down by 2 units, and we get a new parabola that looks like this. All right, our next one, k of x. This time we see our transformation is occurring on the inside, x minus 2. That means that the x changes before we square it. So since x is changing, we know that this has to be a vertical shift. So this is in fact going to be a shift to the right. So it's a little bit counterintuitive, but what we're going to do, in order to enable that shift to the right that this causes, is we're going to add 2 to each of our x coordinates. So I'm going to start with these original ones again, and I'm going to do x gets 2 added to it. So we'll see all of the y's stay the same, but when I add 2 to -2, I get 0. When I add 2 to -1, I get positive 1. 0, 0 is going to shift right over to 2, 0. 1, 1 is going to shift to 3, 1, and 2, 4 is going to shift to 4, 4. So we just took each x-coordinate and added 1 to it, and now our graph looks like this. We have 0, 4, 1, 1, 2, 0, 3, 1, and 4, 4. And we can see that that shift has occurred to the right. Okay, now there isn't any reason that we can't do more than one of these at a time. So let's look at an example now where we combine a horizontal shift and a vertical shift. So here, if we look at this function z of x equals x plus 1 squared minus 4, we can see our horizontal shift, that's the right or left shift, that occurs right here. And so that is going to be a shift to the left by 1. And then our vertical shift is occurring out here. So our vertical shift is the yellow one, our horizontal shift is the pink one. And the vertical shift is minus 4, so that's going to be down by 4. And so if we graph our parent function, our parent is the quadratic, and I know that because I have a square here, and this square here is like, think of the parent function as being the main idea. So it's the squaring function there. And so we know that that has the points 0, 0, whoops, that's not what I wanted, 1, 1, and negative 1, 1, 2, 4, and negative 2, 4. And so what I'm going to do now is I'm going to move each of these according to the shifts that I've got here. So I'm going to take 1, 1, and I'm going to move it left 1, and then down 4. So that point moved right down there. And then I'm going to do that same thing for each point. So the point negative 1, 1 is going to go left 1 and down 4, right there. And then the point 1, 1 is going to go left 1 and down 4, right there. Then the point negative 2, 4 is going to go left 1 and down 4 and end up now as an actually as a x-intercept. And 2, 4 is going to go left 1 and down 4 and be another x-intercept. And we see that our final picture looks like this. So if we want to examine what each of the points is doing, here I'm going to make a list of the points on the parent. Nope, wrote that backwards. Negative 2, 4, negative 1, 1, 0, 0, positive 1, 1, and positive 2, 4. And then our corresponding points, we're going left by 1, so we are subtracting 1 from x, so that's going to take us to negative 3. And then down by 4, we're subtracting 4 from y, so we get to negative 3, 0. And that is this point right here. I had a hard time finding it, but there it is, negative 3, 0. And then negative 1, 1, again, we subtract 1 from x, so that takes us to negative 2. And to go down 4, we subtract 4 from y, so we get to negative 3. For 0, 0, left 1 takes us over to negative 1, down 4 takes us to negative 4. For 1, 1, left 1 takes us to 0 on the x, and subtracting 1 minus 4, we get negative 3 on the y. And then for 2, 4, going 1 over to the left takes us to an x value of 1, and 4 down takes us to 0. So you'll see that each of those points corresponds to one of the black dots that I have over here. Okay, then we have, let's look at this function. P of x is absolute value of x minus 2 plus 3. Again, we're combining two different shifts here. So the first shift, we've got this minus 2. That is horizontal. It's on the inside. It's a shift right or left. And this time we are going to go right by 2. And then we have this plus 3 on the outside. That means we're changing y, so we're moving vertically. And we're going to go up by 3. we have to remember what our absolute value function looks like. So our parent here, p of x, goes through the points, let's say -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. I got each of those by picking an x value and then taking its absolute value. P of x I should have written down is this absolute value of x. And we'll remember that this looks like, has a distinctive V shape. So it's going to look like this. All right. Now we look at our new points. Oh, shift right by 2, which means that we're going to add 2 to x. And a shift up by 3 means we're going to add 3 to y. So to get our new points, add 2 to x, so that takes me to 0, and add 3 to y, that takes me to 5. So I get the point 0, 5 right here. Then add 2 to x, that gives me a 1. Add 3 to 1, I get 4. And now I have the point 1, 4 right here. We can maybe see the beginnings of that V shape taking place. 0, 0, add 2 to x, we get to 2. Add 3 to y, 2, 3, right here. And then 1, 1, we're going to add 2 to x, 3 to y. That's the point 3, 4 right here. And add 2 to x, 3 to y, the point 4, 5. And it's always good to do a quick double check. Let's make sure that these points here actually work in our formula for, I shouldn't have called it p of x. Let's call it r of x. I don't know why they use p there. We'll call this r of x. So p of x, p of 0 is the absolute value of 0 minus 2 plus 3, which is the absolute value of 2 plus 3, which is 5. And we can see that point is in fact the correct one using our formula. All right, now that we've contemplated horizontal and vertical shifts, we're going to look at stretching and shrinking. So the big difference here is that when we shifted, the overall shape of the graphs did not change. So they maintained their shape. They were what we call rigid transformations, where nothing about the shape changes. It just moves over or up, depending on the formula. When we look at shrinking and stretching, we're going to be looking at the overall shape of the graph being different. So it might get wider or skinnier or shorter or taller, depending on what kind of shrink we're doing. So just like before, we're going to contemplate vertical changes first. So vertical changes always mean that something is happening to our y coordinate. We're moving up and down if we're moving vertically. So here, if our function is f of x and we're talking about some positive number a vertical shrink or stretch is going to look like the function y equals, let me use the darker pen, y equals a times f of x. So notice here the a is again outside of the function, and this is going to mean that all of our y coordinates get multiplied by a. So if a is a number that is bigger than 1, remember a is always positive. We'll worry about the negative case in a little while. So if a is a positive number and it's bigger than 1, then this is going to be a vertical stretch. So the function is going to look like it's getting taller. It'll also, in a lot of cases, make it look like it's getting skinnier. If a is between 0 and 1, this is going to be a vertical shrink. But the way we can figure out what the graph looks like is we can take our original y coordinates. So let's say that the graph of a, no, I don't want to use a there. Let's take the graph of, I don't know, let's call it c comma d. If this is a point on our original graph, then when we create our new graph, the point c comma a times d is going to be on the new graph. So these stretches these vertical stretches and shrinks, just multiply the y-coordinate by the whatever value is in front of the function. So an example of this would be something like if we did y equals 2 times the absolute value of x, or y equals 1/2 times x squared. Notice in this case that the squared only belongs with the x, so the 1/2 is on the outside of the x squared. Then we have the corresponding horizontal shrink or stretch. So this is where we're going to be changing our x coordinates, and this is going to happen on the inside of the function. So this would look like y equals f times a of x. And just like before, where when we had a plus inside, it ended up moving us to the left, and when we had a minus inside, it ended up moving to the right. Things are a little counterintuitive here. Here, if a is bigger than 1, we actually have a horizontal shrink. This is going to make things narrower. And if a is between 0 and 1, that is going to be a horizontal stretch. This makes things wider. So some examples of this would be if we had the absolute value of 2x as our function, or if we took that 1/2 and we included it in our squared, that can be considered a horizontal. Well, okay, so y equals absolute value of 2x is a horizontal shrink, and y equals 1/2 x squared, all squared, with the 1/2 getting squared as well, that is a stretch. So this is going 1/2 x all squared is going to be a wider graph than the x squared, whereas y equals absolute value of 2x is going to be a narrower graph than y equals absolute value of x. So here, well, if CD is on our original graph, this time we're going to divide. So again, we're using the opposite operation. C over A times D is going to be on our new graph. All right, so let's look at these two cases here. So here we have 1/4 x squared and 4x squared. So our parent function is x squared. And so we know by now that that goes like this, 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4 to look something like this. Okay, so if we start off with f of x, let me write down those points so we can see what's happening here. Negative 1, 1, 1, 1, 2, 4, and negative 2, 4. I wrote them in a little bit of a weird order, but that's okay. Hopefully we can roll with that. So let's notice in f of x that the 1/4 is outside the parent function. So it means it's going to affect our y coordinates, which means we're going to multiply each of our y coordinates by 1/4 to get a new point. So I'm going to do f of x here. I'm going to multiply y by 1/4. So when y is 0, that doesn't change it, but then I'm going to have negative 1, 1/4, 1, 1/4. So let's graph these and see what this is starting to look like. All right, we said that multiplying by a number less than 1 was a shrink, and you can see that this, so far the picture looks shorter than it did before. 2, 1, and negative 2, 1 are our last 2 points when we divide or multiply that x by 1/4. So 2, 1 is here, and negative 2, 1 is here. So the new graph looks like this. And you can see that it's as if somebody came in and stepped on the top of the original graph and shrunk it down. So this point got shrunk down to that point there. And then 4x squared should result in a stretch. So stretches are going to be taller, and they're also going to look narrower generally, whereas shrinks are shorter but also look wider. So g of x, same idea, except this time instead of multiplying by 1/4, we're going to multiply by 4. So 0, 0 stays put, still right there, it doesn't shift, but then we're going to have negative 1, 4, and positive 1, 4 when we multiply our original points by 4. So now we're here and here, and you can see already this thing is looking taller and thinner. And then we're going to have 2, 8, nope, that's wrong, I multiplied by 4 incorrectly, 2, 16, and negative 2, 16. So I can't even draw those. Those are way up here. So this graph gets really thin and tall very quickly. All right, so that's what happens when the number we're multiplying by is sitting on the outside of the parent function. We change our y coordinates and our graph either grows or shrinks comparatively. In the next two, we're going to see that the number we're changing it by is on the inside. And so that means that now we're changing our x coordinate. Our x coordinates are the ones that are changing. Our y coordinates are going to remain unchanged. So this time our parent function is the square root of x. And let's use some key points there. So 0 and the square root of 0, 1 and the square root of 1. Let's go with 4 and the square root of 2, and maybe 4 and the square root of 4, which is 2, and then 9 and the square root of 9, which is 3. So remember that the square root graph is the one that looks like this. Just plotting those points I just drew. Okay, now our y coordinates aren't going to change. It's just our x coordinates that are going to change here. So for r of x, remember we're multiplying by 5 inside, which means that to figure out the new coordinates, we're actually going to be dividing by 5. This is going to be a shrink of sorts. So for g of x, for r of x, I don't know why I said g of x, our y coordinates don't change, but we're going to take each of our x's and we're going to divide it by 5. And we'll see that that matches up for r of x. So if I divide 0 by 5, I get 0. So that still holds true. Now, if I take 1/5 as my x, and imagine plugging that in, then we have the square root of 5 times 1/5, which is the square root of 1. And so that's why the corresponding y coordinate there is 1. Here, if I take 4/5 and 2, if I plug 4/5 into my function r of x, I'm getting 5 times 4/5, which is 4, and the square root of 4 is 2. So that works. And then this one is going to be 9/5. So our graph looks like this, 0, 0, and then we have 1/5, 1, 4/5, which is just a little bit less than 1, 2, and then 9/5, which is close to 2, 3. So it looks something like this. Okay, so that looks at first like maybe we made it taller, but what's happening here is we're squishing it sort of like an accordion. Imagine squeezing the grade function towards the y-axis, squeezing it in this way, and that's going to map each of those points to its corresponding horizontal shrink. So this was a horizontal shrink when we had the 5 in there. S of x, this other one is going to be a horizontal stretch. So this is going to be as if we take hold of the gray one and we pull it outside. So it's going to end up looking shorter as well, but we're going to be moving the other direction. So this time for S of x, we're going to multiply all of our x coordinates by 5. Put that comma in a weird place. So I'm going to still have 0, 0. So we still start here. That one doesn't stretch. It's fixed where it is. 1, 1 is going to become the 0.51, because if we put a 5 in here, then we have the square root of 5 over 5, and that's the square root of 1, which is, I don't know why I wrote zeros in all of those. That was a little bit weird. Okay, this is going to be 5, 1. If I multiply 4 times 5, I get 22, and that's because the square root of 20 over 5 does in fact equal 2. And now we're already off our graph, but we can do this last one. This one would be the 0.453. So you can see this gets stretched way out. 1, 2, 3, 4, 5, 1, and then it's going to look like this. So you can see that these points are getting pulled out there. Okay. So those are stretches and shrinks. Now, this example, we don't actually have a formula for the function. We just know that we want to graph f of 4x. So to note, what we notice here is that the 4 is on the inside. So this is going to be a change to the x values. And because it's a change to the x values, it looks like we're multiplying them by 4, but what we actually want to do is divide them by 4. So this is going to be a horizontal shrink. And I really like this example because I always talk about the shrinks being like an accordion, and because of the bends in this one, we're actually going to get to see that accordion thing happen. So what I'm going to do is I'm going to make a list of all of the points on this graph to the left. I'm going to label them A, B, C, and D. And I'm going to say A is the point, what is that, -3, -1. B is the point, -1, 1. C is the point 1, 2, 3, 4, -3. And D is the point 6, 3. All right, and we're doing a horizontal shrink, which means our x values are changing. We're going to divide them by 4. So over here, I'm going to have new points, A prime, B prime, C prime, and D prime, that correspond to those other points that I get by shrinking by a factor of 4. So I'm going to get -3/4, -1, -1/4, 1. Divide 4 by 4, I get 1, -3, and then divide 6 by 4, and I get 6/4, which is 1.5. So we'll call it 3 halves. So 6/4 is the same as 3 halves, 3. All right, so now if I plot those points, A prime, -3/4, -1 is going to be about here. -1/4, 1 is here. 1, -3, all the way down here. And 3 halves, 3 is right about here. And we're going to connect them in order that we drew them, so we're going to get lines that look like this. And now you can see that this was a shrink. We shrunk it when somebody came along and just squished them together, and now we have this new graph that we got by taking f of 4 times x. Okay, our last transformation is going to be reflections. So this is where we can introduce negative signs. All right, so if you think about it, if we have a function y equals f of x and we want to reflect it across the x-axis, that means that everything's above the axis goes below it, and everything that's below it goes above it, which means that the coordinate that's changing is our y-coordinate. And we've seen in all our previous examples that when we're changing the y-coordinate, that change happens on the outside of the function definition. So to reflect across the the x-axis, we're going to put the negative on the outside. Look like that. And what ultimately we're going to do for each point is we're going to multiply the y-coordinate by -1. Similarly, but also opposite, reflection across the y-axis. If we're reflecting, the y-axis is acting like our mirror. That means everything to the left moves to the right, everything to the right moves to the left, which means that it's our x-coordinates that have changed. And we know in that case, the change happens on the inside of the function definition. So here we're going to have f of -x. And we're going to be multiplying our x-coordinates by -1. All right, so let's look at an example here. We have this function here, and we have y equals -f of x. So this is reflection in the x-axis. All right, so the x-axis is now going to act as a mirror. All of our y-coordinates are going to be, that are positive, are going to become negative, and all of the ones that are negative, which there aren't any in this case, are going to become positive. So it's going to look like this. So if I take this first point in the middle, that's one stays there because it's on the x-axis, so it doesn't move. The point here at 1, 1 is going to get reflected down to 1, -1. We're multiplying y by -1. Then this third point over here in red at 1, 2, 3, 3 is going to end up at 3, -3. And then lastly, the point that's at 4, 1 is going to end up at 4, -1. And we get a picture that looks like that. Over here, y equals f of -x. That is going to be a reflection in the y-axis. So now all of our y values are going to stay the same. So we're going to stay above the x-axis as in the original picture, but now we're going to flip to the left side of the graph. So again, that first point there at the origin stays there. The point 1, 1 becomes the point negative 1, 1. The point 3, 3 becomes the point negative 3, 3. And the point 4, 1 becomes the point negative 4, 1. And we get this picture here. So just changing x's to negative x's where required, or y's to negative y's. So these ones are pretty straightforward, pretty easy to understand. And notice that just like the shifts and the shifts right or left and up and down, the shape doesn't change, right? The shape is held the same, but the position of the thing moves. All right, so let's look at a summary of all of this. So this chart here is a good thing to refer back to. It tells you what replacements you're making each time and which direction you're going. I think the most important thing to remember from all of this is just a nice simple way to review everything I just said, but the most important thing is this chart down here, which tells us that we have to do these things in order. This is important. So the first thing we're going to do is any horizontal shifts. So these are x plus or minus c's goes first. Those go first. Then after that, we do any horizontal or vertical stretches and shrinks, and it doesn't matter which of those you do first. So this is where we have c times f of x or f of cx. Those happen next. Then we do any of our reflections. So those are negative f of x or f of negative x. Those come next. And then the very last thing we have to do is the vertical translation. If you do a shift up or down too soon, especially when you have a reflection involved, you're going to end up with a picture that looks incorrect. So horizontal shifts, then we do our stretches and shrinks, then we do our reflections, and then last we do our vertical shifts. So let's look at this graph here that puts them all together. Okay, so we have f of x equals 2 times absolute value of x plus 1 minus 3. And we're told this time that the parent function is absolute value of x, and we know that that has some points. We have 0, 0, negative 1, 1, 1, 1, negative 2, 2, 2, 2. That should be a sufficient set to kind of give us a sense of what direction we're heading. So let's look at this. So the first thing we want to look for, since it's our first step, is whether or not we have a horizontal translation. And we do. We've got a horizontal translation right here. So that translation, we are moving left by 1. Left by 1. So that means that all of our x's are going to we're going to subtract 1 from them. So I'm going to go ahead and write as if that were our only transformation. If we only did left 1, where would we end up? And that would be at negative 1, 0, negative 2, 1, 0, 1, negative 3, 2, and then 1, 2. That's our shift left 1. But then we can see that next we look for stretches or shrinks, and we've got this right here. It's on the outside, which means we're changing y. So here we're doing this one's going to be a vertical because it's changing y, and it's multiplying by a number bigger than 1, so it's going to be a vertical stretch, which means we're going to change all of our y's, by 1. We're going to multiply all of our y's by 2. So we started off with these points here. They all turned into the ones listed under the words left 1. Now we're going to change those points, the ones that are under left 1, we're going to change those to account for the vertical stretch by 2. So now we're going to multiply all of the y coordinates by 2. So the first point, 0 times 2 is still 0, but then the next point we have a 1, so that's going to become a 2. The next point also has a 1, which becomes a 2. And then the last 2 points have a y coordinate of 2, so that is going to become a 4. All right, and then we have no reflections. There's no negative signs in front of the x or in front of the whole function, so no reflections to deal with. So lastly, we look for our vertical translation or vertical shift, and we see that right here in the minus 3. So that one, we're going to shift down 3. And that means we subtract 3 from our y coordinate. So we're going to take negative 1, 0 and shift it down to negative 1, negative 3. Negative 2, 2 is going to shift down to negative 2, negative 1. Subtracting 3 from all of my y values. 0, 2 becomes 0, negative 1. Negative 3, 4 shifts down to negative 3, 1. And 1, 4 shifts down to 1, 1. Okay, so what we should see when we graph this is a graph that is a little bit to the left, is vertically stretched, so taller or skinnier. That's the second thing we'll see in our graph. And then we're going to check to see that it's also been moved down when we graph these points. So we've got negative 1, negative 3, that's right here. Negative 2, negative 1. 0, negative 1. Negative 3, positive 1. And 1, 1 right here. All right, and if you look at this graph and compare it to the one over there on the right, you will in fact see that it is shifted left, shifted down, and it's a little bit skinnier, which is the same as being taller, which is what that vertical stretch did to it. All right, let's do one last example. This one has a lot of transformations in it, which means that it's tricky. There's a lot of places to make some mistakes, but we're going to take them one at a time and see what we can come up with. So first of all, we're told that the parent function looks like y equals square root of x, and we already know that if we look at our parent function, we can consider the points 0, 0, 1, 1, and 4, 2. If we wanted to do 9, 3, we could do that as well. Let's go ahead and do that just because why not? Okay, so remember the order is of horizontal shifts, then any stretches or shrinks, reflections, and then last we do vertical shifts. And for the stretches and shrinks, it doesn't matter. If you have more than one, it doesn't matter which order you do them in. So, all right, so first thing we're looking for is a horizontal shift. To see the horizontal shift a little bit more easily, I'm going to write this guy like this. No, not like that. I'm going to switch around. I'm going to write it as negative x plus 3. That, for me, makes it a little clearer that we have a horizontal shift plus 3, which means we're going to the right by 3. No, that's the left. Plus 3 means go left. So we're going to take each of our x's and we're going to subtract 3 from it. So 0, 0 ends up at negative 3, 0. The point 1, 1 is going to end up at the point negative 2, 1. 4, 2 is going to end up at 1, 2. And 9, 3, subtracting 3 from that, we get 6, 3. So horizontal is changing the x coordinate. So we subtracted 3 from all of our x's. All right, that's the only horizontal shift. So now we look for stretches or shrinks, and we can see we've got one right here, 1/2. That 1/2 is going to be a vertical. It's on the outside, so it's a vertical shrink. We're going to multiply y by 1/2 to figure that out. We're changing the y coordinate because it's on the outside. We're going to change it by a factor of 1/2. So all of our y's get changed by 1/2. So we get negative 3, 0, because 0 times 1/2 is 0. Negative 2, 1 times 1/2 is 1/2. 1, and then 2 times 1/2 is 1. And here we get 6, 3 halves. There. All right, no other shrinks. So now we look for reflections. And we've got 2 of them. We've got 2 of them. So we're going to take them one at a time. Let's start with the one on the inside. That negative x right there, that is a reflection in the y-axis. It tells us to take all of our y-coordinates and make, all of our x-coordinates and make them the opposite sign. Multiply them by negative 1. So we're going to get 3, 0, 2, 1/2, negative 1, 1, and negative 6, 3 halves. All right, last but not least, we've got one more reflection, hanging out on the outside there, right out here, that is a reflection in the x-axis. So that is going to flip this thing over the x-axis, making all of our y coordinates 0, or negative, I'm sorry, not negative. It's going to change all of their signs. It's going to change all of their signs. So we're going to end up at 3, 0. We're going to end up at 2, negative 1/2. We're going to end up at negative 1, negative 1. And we're going to end up at negative 6, negative 3/2. Okay, before we plot it, let's just do a reality check to see if these points actually work in that formula. The points that we got by following the path work in our original formula. So we have z of x equals negative 1/2 times the square root of 3 minus x. Let's look at z of 3. By the math we did up here, we should end up with 0 because we've got the point 3, 0. Right, we're looking for, so we should get that z of 3 is equal to 0. So z of 3 is going to be negative 1/2 times the square root of 3 minus 3, which is negative 1/2 times the square root of 0, which is in fact 0. Let's pick one other one. Let's do z of negative 1. We have the point negative 1, negative 1. So let's see if z of negative 1 actually turns out to be negative 1. We get negative 1/2 times 3 minus negative 1, or the square root of that rather. We get negative 1/2 times the square root of 4. That's negative 1/2 times 2, which is in fact negative 1. So our points make sense with our formula. So now let's plot them. We've got 3, 0. 1, 2, 3, 0. 2, negative 1/2. Negative 1, negative 1. And negative 6, negative 3/2. So we can see here the combination, that's a terrible line I just drew, but you can see the combination of the vertical, the shift to the, our shift to the left ends up, because we also reflect in the y-axis, ends up being a shift to the right. So the shift to the right is a result of the shift left plus the reflection. It's underneath the x-axis because of the reflection in y, and it looks like it's been squished down a little bit because of our vertical shrink.